the eloquent introduction. It's a great pleasure and a great honor to be here and to give this talk. All of the math that I'm going to talk about today is inspired by Dennis's beautiful work on renormalization. Fortunately, Misha has already set the stage for me in his lecture, so I don't have to show you my slide with the two fishes and the thermometer. You're already convinced that renormalization is important, and you have some understanding of what it is about. So I can go straight to business and define, and most of my talk will be about renormalization of critical circle maps. Some of it will be about the applications, and always in the setting, before I can define the critical circle map, I have to define the circle. So the circle is, for the duration of this talk, is the affine manifold is the quotient of R mod Z. In a critical circle map, the letter is large enough? Yes. So a critical circle map will be a homeomorphism of the circle. Smooth. Let's say C3, the 2 plus epsilon if you like. It will have a single critical point. For simplicity, I'll always put it at 0. And this critical point is non-flat. And again, for simplicity, we'll assume that it's cubic. So the map near this point looks like A x cubed plus B. Now, all of these assumptions can be weakened. You know, you could look at finitely many critical points, and you could raise the order of criticality as long as they stay non-flat, and that makes life more.
What does the critical point?
Oh, that's where the derivative vanishes.
You read
but it's smooth.
Draw the graph.
Yeah, I'm going to write a formula, in fact, if you like. So here's.
When you say you like the cubic, you mean you can do something else than odd powers?
No, I don't mean that. That I don't mean. Right. Okay, so well, might as well. So here's a useful formula. This is a well-known one-parameter family of critical circle maps known as the Arnold's family. These analytic maps, like I said, it's a one-parameter family. Look at the map of the real analytic map defined by A theta of x, which is x plus theta minus 1 over 2 pi sine 2 pi x. So this maps R monotonely to R, has cubic critical points at integers, and commutes with the unit translation. And therefore projects to a well-defined critical circle map f theta, which maps the circle to itself. Okay? Now, the renormalization of critical circle maps serves to explain a universality phenomenon which was observed in the 1970s. I don't actually know, so I know the two papers in which renormalization was defined. One was by Ostlund, Brand, Setna, and Sijje, and the other one was by Feigenbaum, Kadanoff, and Schenker, and the definitions were similar. But I don't know, maybe you can tell. Schenker was the first one to observe this. Okay. So here's the universality. Let's take a one-parameter family, for example, this one, which monotonely depends on the parameter. And let's look at the rotation number. Oh, well, maybe I should remind, well, I guess I shouldn't really remind you what the rotation number is. So let's look at the rotation number as a function of theta, right? So, theta maps to rho f theta. So this is a monotone function.
When Deline talked on the Shelburne man's work on the Boulevard Key, and at the same time, he said that the rotation number was look at the combinatorial structure of the orbit of a point. It has no periodic points, and there'll be unique irrational rotation whose orbit has the same combinatorial structure.
That's a theorem.
That's the definition.
That's a definition. Yeah, I suppose you could take that as a definition. Except that leads into trouble in the rational case. Yeah. Okay. Anyhow, so this is a monotone, but not a strictly monotone function. You know, the graph is a double staircase. You have intervals for rationals and points for irrational values of rho. And so now look. So pick your favorite quadratic irrational. So I'll take the inverse golden mean. So let rho star be root 5 minus 1 over 2. So this is expressed as a continued fraction in which all terms are 1. To save space, I'll write such fractions in brackets. Now, consider the sequence of rational convergence of this continued fraction. So that would be Pn over Qn rho n, which is given by the fraction with n ones. So for each of these rotation numbers, you have an interval of thetas for which you have this value of the rotation number. So I don't know, call it In. This is the set of theta such that rho is Pn over Qn. So these are intervals which converge to the unique parameter value theta star, which corresponds to this rotation number. So the observation is that the length of In is a delta to the minus n, where is asymptotic to delta minus n, where delta is a universal constant. That is independent of the family. Okay, so let me describe the renormalization picture, which explains this, in particular, explains this universality phenomenon. So let me define the renormalization operator for you. Now, from Mishra's talk, you already know that renormalization is nothing but a rescaled first return map. So we should look at the rescaled first return map somewhere on the circle. Now, it's convenient when defining the renormalization to remember that there is a marked point on the circle, which is the critical point. Now, what was this thing? You go around the circle over and over and you don't know when to stop, right? So if you want to stop when you come close to the point 0, you'll be defining a sequence of closest returns to the origin. And there is a particular subsequence of that sequence, which is given by the denominators of the rational convergence of the rotation number. So if your rotation number is given by a continued fraction, a naught, a 1, etc., a n, etc., finite or infinite, if you take a convergent Pn over Qn, obviously you have to have at least n terms to look at this one. Then the denominators Qn will be will correspond to closest return times of points on the circle. So in particular, since we mark the point 0, this would be the closest return times of the point 0. So if this is determined fqn of 0, in this interval between 0 and fqn of 0, there is no smaller return. And then the next return of this type occurs on the other side. The rotation number is irrational, then you have an infinite sequence. Now, when renormalization is defined, for historical reasons, I guess, one considers the first return map of such an interval. The first return map of the arc of the circle between two closest returns of this type. Now, if you look at this interval, it's an exercise to figure out what the closest return is. And I'll tell you. It's piecewise defined. On the orange interval, it's determined fqm, which translates it over like so. And on the blue interval, it's determined fqn plus 1, which translates it over like so. This is the same point, by the way, qn plus 1. And this is the first return map, well, of the interval. And now, all that remains to define renormalization is to rescale this first return map. So we recover the circle map. You run into a bit of a problem here. It's easy to figure out how to get the circle out of this. You should use the orange map as a chart, as a local chart to identify points here with points here, and then this projects to a well-defined map, well-defined homeomorphism. Problem is that the identification here, it has the same smoothness as f. So under my assumptions, it's C3. Even if f is analytic, it will not be affine. So you don't recover a circle. What you do recover, if you use this gluon, is a circle up to a smooth change of coordinates. So you don't recover a well-defined circle map. What you recover is a smooth conjugacy class, which is a problem. So there is a simple solution to this problem, which is don't glue, don't recover a circle. Instead of working with circle maps, work with pairs of interval maps. And this leads to a formalism of commuting pairs. Well, in this case, these pairs of maps commute just because the iterates of the same map. And then to rescale this, I'll just rescale the larger of the two intervals to the unit size. So I'll take the linear rescaling, which sends 0 to 0, this point to 1, this point, wherever it happens to fall, and I'll get a pair of maps, which I'll call the nth renormalization of f. Okay? So now, scaling is just linear. Okay, just a linear map. Okay? 1 over fqn of 0 times x. That's your rescale. Okay, so here is a conjectural picture which explains the universality in particular, and it's full. So for the golden mean, it appeared in the first and the two papers that I mentioned. But in full generality, it was formulated by Oscar Lanford in the early 1980s, and it's known as the Lanford's program since then.
If you just rescale one side, why do they still compute?
No, I rescaled both sides.
Oh.
I rescaled both sides.
Rescaling so that the y-stat
rescale so that the right side becomes of size 1. Would also rescale in some other way, say that the total length is 1. In fact, it's not even essential that this particular interval is taken to define the first return map. None of this is really crucially important. Okay, so here is a conjectural picture. It's a caricature, which in particular will explain the universality. So let's imagine the space of critical circle maps as an infinite dimensional cylinder. So it's some space S times the circle. Now, you should think of these maps, you should think of the circle coordinate playing the same role as the parameter theta here. That is, you should think that these are some sort of base maps, and then you obtain any map just by rotating the map in S, just by composing with the rotation. Okay? So, now, in this space, how is renormalization defined? Well, what's S? What's S? Oh, who knows? Like I said, it's a caricature. It's just an infinite dimensional space. This picture doesn't really exist.
T is a circle and S all the way to the parameter.
Yeah, except there is no reason to think that we can split. I mean, it's not, life is not that
Theta
simple.
is a T and the other parameter.
Yeah, yeah.
It's like a space with a circle action, yeah?
It would be good not to read too much into this picture. So it's an attempt to visualize this space by splitting off a smooth coordinate which controls the rotation number in a monotone way. Okay, so you should think of this coordinate as simply rotating the circle in positive direction.
So it's not necessarily the rotation number of the map.
No, it won't be the rotation number of the map. The rotation number will depend on this parameter in exactly the same way as the rotation number depends on the parameter here. You will have a devil's staircase over theta. Okay? Now, if you look at how renormalization is defined, maybe it's useful for me to take a quick step back and say what renormalization does in the rotation numbers. Now, like I said, this pair can be viewed as a smooth conjugacy class of circle maps. So the rotation number would still be well defined, even though the circle map itself is not well defined. And it's an easy exercise to see that renormalization acts as a Gauss map on the rotation numbers. So the renormalization of the rotation number of the renormalization of F is G of the rotation number of F, that is the fractional part of 1 over the rotation number of F. In other words, if this, well, the Fra of F is a continued fraction A0, A1, etc., then this thing just forgets the first digit, right? So then this is equal to A1, A2, etc. It also tells you immediately which ones are not renormalizable even once. It's the ones for which the rotation number is 0, so the first digit here is infinite, if you will. Okay, so now as we look at this space, let me define by S sub n the slice or the strip in this cylinder in which the continued fraction starts with n. So these are the maps such that ρ of F has a continued fraction in which the first digit is n. N here could be infinite. So n is either a natural number or infinity. Okay? Now, like I said, the circle coordinate controls the rotation number, so you would have this cylinder partitioned into vertical strips. So here is S infinity, 0, S1, S2, etc. This goes around. Sn accumulate on a hypersurface here. Now, renormalization is just a rescaled iterate. On each of these strips, the iterate will be constant. So, renormalization is defined as a piecewise analytic map here. And the conjecture, very similar to the picture with the, how Kurt put it, French fries that Misha had. The conjecture is that the map is hyperbolic. It's strictly contracting in all of the directions except the circle direction. And the circle direction is expanded to cover everything. Indeed, if you look at this on the level of the rotation number, if you forget the first digit, you could get anything. Right? So in the direction of the rotation number, if I look at the image of the strip, what is S0? I have no idea. There is no S0. S1, S2, S3. If you look at the image of the strip S1, then in the circle direction, this should cover everything. And the conjecture is that there is a uniform expansion here and uniform contraction in all the complementary directions. So this would be the image of this rectangle by renormalization. And the same would happen in every other strip. So say in S2, you would have the same thing. S3, etc. So the picture that you get is a picture of an infinite dimensional Smale horseshoe. There is going to be a horseshoe attractor here with one-dimensional unstable direction, which is this direction of the rotation number. Okay, all other directions are stable. And in particular, in this horseshoe, there will be a map in S1, which is a renormalization fixed point, call it F star, which has rotation number equal to the inverse golden mean. And this has a one-dimensional unstable direction, four-dimensional one stable manifold, and then if you want to explain this delta, well, it's the usual thing. If I now start taking pre-images of this cylinder, I'm going to get, of this strip, by this branch of renormalization, I'm going to get tall and narrow strips, and my one-parameter family crosses this transversely. The rate at which these strips shrink is exactly the unstable eigenvalue here, which is delta. And the intersections of my one-parameter family with this strip are precisely those intervals. So that explains the golden mean universality, but the same picture encodes many other universalities as well. So this is the global conjectural picture. Okay? All right. So now let me do a quick run through the proof. So first of all, this picture is a theorem. Okay, so the theorem is a product of a work of many people. I'll mention some, but there are probably some others that I won't mention. And I'm still looking. Yeah. Okay. So all right. So the global horseshoe picture is a result of my own work, and I hope to at least sketch some of the ideas which go into this. Okay. So the first the first step to proving this renormalization picture and finding this horseshoe attractor, and in particular finding this fixed point, is known as real a priori bounds. And this is the statement that if you take a map F whose rotation number is irrational, and you start renormalizing it, then this is precompact. This sequence is precompact. So you can actually pass the limits. You expect to find that it converges to some subset of the horseshoe. So at least this means that you can pass the limits. In this case, this is the theorem of Hermann and Schwantek and Hermann in chronological order. And it says that it's precompact. C naught would be enough, but in fact you can get C2 if you assume C3. Now, once it's precompact, you can start worrying about the limits. And here there's a very nice understanding of what kind of limits you can get from the work of Henri Epstein. So the limit points live in what's known as the Epstein class. First of all, these maps are analytic. They're real analytic, and they have very nice complex analytic extensions. Remember, these are maps of the intervals. So on the real line, you just take an interval, and the map would map it to some other interval. But in fact, the inverse of this map can be extended to a plane, to the complex plane with two slits on the sides of this interval. So this is a rather rigid class, and all limit points live in this class. Now, the next step, so this is the same as the theory for unimodal maps that Misha is describing in his lectures. But the next step already diverges with unimodal maps. So in the unimodal case, you have Doherty-Hubbard quadratic-like extensions to define complexified renormalization. In this case, complexified renormalization was defined by a student of Dennis, Faria, in his thesis, and the extensions are called polymorphic commutant pairs. And I'll draw you a picture of what a holomorphic commutant pair is. So what are the colors I use? Orange and blue. Okay, so here's my pair of maps. And a holomorphic commutant pair is an extension of this picture to the complex plane of the following form. It looks like a butterfly. So here, this map, which is our iterate F2n, extends to a wing, real symmetric one, which contains this interval. The blue one does the same. The range of both of these maps is the same disk, call it delta, which strictly contains this picture in the interior. And just so the domain actually contains a neighborhood of the origin, we are going to put in the middle a little disk in which the map is the composition of the two. So these objects are holomorphic commutant pairs. These are the appropriate extensions of this picture to the complex plane. And the next step in the renormalization theory, the development of the renormalization theory, is to show that you actually do get such a picture for sufficiently high renormalizations of maps in the Epstein class and with some bounds, so that you can actually do this. And this statement is known as complex a priori bounds. And the theorem says that if rho f is irrational, then there exists a knot such that for all n greater than or equal to a knot, Rnf has a holomorphic commutant pair extension. Moreover, if you have f and g with the same rotation number, then the holomorphic commutant pair extension of f is quasi-conformally conjugate to the holomorphic commutant pair extension of g with a universal k. Now, this statement for bounded type rotation numbers, that is rotation numbers in which you only take a finite number of strips here rather than the whole horseshoe, is also part of Edson de Faria's thesis, and its proof is based on Dennis's sector lemma, for those who know the subject. And in the general case, the proof is mine, and it's based on a method which we developed with Misha for complex a priori bounds of quadratic maps. But there is a subtlety here. There is a difficulty which is worth mentioning, because it's sort of the same kind of difficulty which is going to be a problem in a couple minutes. If the rotation type is unbounded, then it's not enough to control the geometry of this picture. It's not enough to control the modulus of the annulus, of the complementary annulus, of delta minus this stuff. Because there is another place where you come close to the boundary of the domain. And these are the slits on the real line, right? You do have them from the definition of the Epstein class. And what could happen is that the geometry could degenerate not from coming close to the outer boundary, but to coming close to the slits. So you actually have to, and this will happen, so you have to control this degeneration to show that it's the same for all maps of this type. Okay, then once you have quasi-conformal conjugacies, then you are in business, and you can prove the...
question, sorry.
Yes?
So in complex priori bounds, the map F is just initial settlement?
No, of course not. I mean, sorry if I didn't make this clear. At this point, we're working with maps of Epstein class. Oops. Whoa. It didn't warn me that it was still alive. It's dangerous. I should have used slides.
Thank you for using the board.
You're welcome. Okay. All right. So the next step in the story is the existence of the horseshoe attractor. A. And so on here, as usual, the dynamics is parameterized by a two-sided shift.
What do you have to control the slit over there on the left, on the real axis?
So why is it there?
No, is that what the piece you have to control?
Yes. So what you have to control here is the situation when preimages of a disk are going to come close to the slit. And this will actually happen if the continued fraction is unbounded. It does happen. And then the key is to show that, in fact, it happens in a nicely geometrically controlled way. You sort of have a nice kind of curve. Yeah, there's a nice little toy picture, which sort of looks like this locally. It has the same parameters. It's degenerate, but it's degenerate in the same way if the rotation numbers are equal. Yeah, so there is a quasi-conformal model for this. Yeah, but it's a little wrinkle here, which actually causes a lot of grief once you start proving it. Okay, so the existence of the Horseshoe attractor A and the statement that for any f in the Epstein class such that the rotation number is irrational, the renormalizations converge to this attractor. For bounded type, the proof was given in Edson's thesis, and this is the main content of Edson's thesis, and it's based on Dennis's theory of Riemann surface laminations for such dynamicals, well, appropriately modified for holomorphic commuting pairs. Then Edson and Wellington de Melo gave a proof using Kurt McMullen's framework of towers, also for bounded type. So bounded type, again, just means that you take finitely many strips in this horseshoe picture rather than taking the whole thing. And then I proved this in the general case, and it's interesting that in the general case you have to control the degenerate situation, which is what you get in the limit when n goes to infinity. Remember, these strips actually accumulate somewhere where renormalization is not defined. It's not defined on S infinity. The rotation number here is 0. But you do get this in the limit. And it's the limit in picture that we're trying to describe. So there is a way to define renormalization appropriately on this strip, but actually on this hypersurface. It blows it up to a thin annulus, just like all the others. This is called the parabolic renormalization. I think Mitsu is going to talk about a version of this. The proof in the infinite dimensional case, in the unbounded case, is a mix of Kurt McMullen's towers and another kind of towers by another student of Dennis, by Adam Epstein's towers, which are actually towers for maps of this type. Okay, but I realize that I haven't given you any flavor of the proofs, and let me concentrate on one. Well, once the attractor is constructed, you still have to prove that it's hyperbolic to complete the proof of this picture. You still have to embed this attractor in some sort of infinite dimensional Banach space in which your renormalization operator is at least differentiable. It's good if it's analytic. And you have to prove something about its derivative. You have to prove that this is actually expanding in one direction and contracting in the others. The thing is, somehow the expanding direction is no trouble in the critical circle maps case. It's the same as this is a huge contrast with unimodal maps because you know what's going to be expanded. It's the direction of the rotation number. If you take your circle map and you take a vector field which pushes the graph up, this is going to be amplified if you take an iterate. The trouble comes before that. The trouble comes with embedding this into a Banach space, a Banach manifold. Problem is that these pictures, all of them, they have an essential flaw which comes from our original discussion. The reason we were forced to not to glue back into a circle, but consider pairs of interval maps. This picture does not complexify well. If you consider perturbation of these maps, which does not preserve the real line, there is no reason why you would still have invariant slits or invariant intervals, and you would still be able to use this machinery. And in fact, you won't. So here is one solution of this, which is
it's not possible to go back to the intrinsic viewpoint, take the natural quotient, the natural structure, all that.
Yeah, so this is what I'm going to describe a way to recover a natural structure, which turns out a posteriori to be natural in many other contexts as well. So here is a way to recover the natural structure. Let's imagine. So here is my circle. Here is the origin. Here's my iterative, I don't know, Fn of 0. I would like to glue this back somehow. I would like to take an interval like this, glue this back into a circle, so the iterative Fn plus 1 projects to a map of this circle. And I can, if I want to look at this on the real line. Now, suppose I look at this in the complex plane and assume that I have the full-on, there's no reason why, but assume that I have the full-on picture. So I assume that I have two fixed points for the iterative Fqn, one on the upper, one on the lower half plane, and that I can connect these two by a curve whose image is another curve which connects the two, and such that the quotient of this, well, the quotient of this, assuming the map is nicely extends, topologically is a cylinder. But assume also that this is conformally a cylinder, not just any cylinder, but the cylinder C mod Z. So assume that this projects, so I don't know, I'll call this C, maybe this picture. So assume that C mod Fqn is the Riemann surface C mod Z. Okay? So this projects to the cylinder. Okay, so if it projects to the cylinder, this interval projects to the equator of the cylinder, 0 projects to some point on the cylinder which I could rotate to 0, and I have a map which is just the iterative Fqn plus 1. Right? The iterative Fqn plus 1 projects to some map G here. G is the projection of Fqn plus 1. Now the funny observation is that if you could do this, then this is not a conjugacy class of maps. This is a uniquely defined analytic map of the circle. And the reason is there are no complex analytic self-homeomorphisms of the cylinder apart from the linear ones. Once I normalize the situation by rotating this point to 0, that's it. There is no more flexibility. So even though my map, which glued this to this, was just analytic, right? I get an affine circle out of this. So I solve the initial problem. This recovers the structure. And this picture is something I call cylinder renormalization. So this map G would be the cylinder renormalization of that. And then the theorem is that for any map F in the Epstein class, there exists n such that n naught, such that for all n greater than or equal to n naught, F is cylinder renormalizable with the corresponding period n. So you can actually do this. You can always do this. And now life is great. Now we're back to real analytic maps. Complex a priori bounds just tell you that there is some annulus of a fixed modulus in which this map is defined. You want a Banach manifold. So this is a Banach manifold. Renormalization is obviously analytic, real analytic. You can take derivatives and then you can prove the general hyperbolicity of the horseshoe. Okay? Now, in the remaining n minutes, I'm going to tell you about some other applications of the same idea, of the cylinder renormalization idea, which go beyond critical circle maps. You know what? Before I do this, let me mention something else. Let me mention some other connection the renormalization of critical circle maps. That's an aspect of renormalization which is not present in unimodal morphisms of the circle. Differs, not maps with the critical points. Via renormalization, that's originated, I don't know, probably in the works of Clarion Sinai and Hermann on circle diffeomorphisms. And let me wave my hands and describe a picture to you. Let's fix the rotation number. Okay, let's fix the rotation number at the golden mean. And let's look at all smooth circle maps, because rotation number is the golden mean. And let's pretend that's a manifold. It's not, but let's pretend. So, in there are diffeomorphisms. And you can still consider renormalizations on diffeomorphisms. And Km result in this setting says that as you renormalize diffeomorphisms, you converge to the trivial case. You converge to rotations or Möbius maps, depending on how you normalize your renormalization. So there is a globally attracting Km fixed point in the differs with the golden mean rotation number. And then there is a codimension 1 submanifold in there, which is the critical circle map. And you have a saddle in that space. That's this fixed point. Okay? You don't see these directions there because I fixed the rotation number, but you see the direction of losing the criticality, losing the critical point. So, and in there you have geometric convergence to this fixed point. So this is sort of a degenerate Km type result. All right, so now let me talk a little bit about other applications of cylinder renormalizations. And I'll try not to say too much because I believe that Mitsu is going to say much more about these things. So, one immediate
How do you go from a non-secular map to, by renormalizing, getting a critical point? I don't know that.
So you mean on my hand waving?
No, it's not that.
Oh, I'm here?
You have renormalization for a non-secular map, and somehow you have a degenerate.
So wait. So here everything is singular. Here everything has a critical
Yeah,
point.
right, right. But then you said an application was taken as a smooth map, right? I mean,
Ah, okay. So no. So this is complementary to this picture. So if you look at the renormalization of differs,
Yeah.
right? If you fix a nice rotation number, then you'll converge to the Km fixed point, which is just the rotation.
Right.
So this is like a codimension 1. This phenomenon lives on the boundary of the differs, and this is codimension 1 surface. So if you don't worry about different kinds of renormalizations, but if it's just one type, just one rotation number, say just this one, then this is like a hypersurface.
But like if you thought sine family, the coefficient.
Yeah, exactly. Precisely, yeah.
In fact, it's more like the result of the limit where it improves that there is universality for all rotation numbers, where they are minor, so that is more for some special needs.
Okay. Yeah, so I
See, this is you think this is the boundary of
yeah, so I'm thinking of this point. Exactly. So I'm thinking of this point as a saddle, which sits in this hypersurface. The unstable direction is losing the criticality, just putting the coefficient there, right? And you have a globally attracting diffeomorphism fixed point, which is just rotation in the Km case, and this is a non-trivial fixed point. In fact, this paradigm. Okay, so in the critical circle case and the circle map case, there are all these complications. Commuting pairs. How do you choose the rescale and etc. But one can do exactly this with renormalization of say Hamiltonian vector fields. Then you really do get the same definition. And there is a trivial and non-trivial fixed point, the Km type and non-Km type. There are not many theorems, but the definitions are there. Okay. All right, so just a few more words. one can apply the same idea to Siegel disks. So instead of renormalizing circle maps, the cylinder renormalization is nicely suited for renormalizing maps with Siegel disks. In this case, there was a renormalization fixed point. Let me now only talk about the golden mean, just for simplicity. So there was a renormalization fixed point constructed by McMullen, who used holomorphic commuting pairs, which are a variation of the Faria's holomorphic pairs. So the pairs that Kurt used, well, let me just draw you a picture. If this is the Siegel disk, so we're talking z squared plus e to the 2 pi I theta z, or z as they say in these parts. This is the Julia set. The rotation number is the golden mean. So this is theta star. And so what you get, instead of an invariant line segment, well, instead of invariant interval, you have an invariant arcs of the quasi-circle, which is the boundary of the Siegel disk, and you still have appropriate extensions of iterates to the complex plane. So in this setting, Kurt proved the existence of the fixed point, and we could use the same formalism, the same cylinder renormalization to define, to get from here a fixed point of the cylinder renormalization for Siegel disks. Okay? So this would be one end of the cylinder, there would be another end somewhere here, and you would have fundamental domain like this. This would project to a cylinder. The end of the cylinder would be would correspond to the origin. So I could just uniformize my cylinder as a punctured plane, send them 0 in that picture to 0 in this picture, and I'm going to end up with a new Siegel disk. This is a new renormalized map G and a new Siegel disk, and the boundary of this Siegel disk is a projection of a piece of the boundary of the original Siegel disk. And you're going to get a fixed point of this renormalization as well. Now, proving hyperbolicity is not easy, so this can be done using the results of Ino and Shishikura, and I'm sure that Mitsu will talk about this on Saturday. And so there's a lot of things that a lot of people are sure that you'll talk about this. Are you taking notes? So using the theorem of Ino and Shishikura plus these techniques, one can show that this is actually a hyperbolic fixed point just in the space, again, of analytic maps. In this case, analytic maps are simply defined in some fixed neighborhood of the origin. So they all have Siegel disks.
Good question. What do you
Yeah.
think about the statement that the boundary of Siegel disks is rectifiable curve?
Well, in this case, it's true.
Oh.
Oh, wait, rectifiable?
Yeah.
It folds in this case, I think.
Oh.
Yeah, it's false, yeah.
Looks rectifiable.
No, it's self-similar, Dennis, so it doesn't
Yeah.
look flat anywhere.
Oh.
It's sort of, you know, uniformly wiggly. It's a quasi-circle. It's a theorem.
Self-similar to what now?
Under renormalization.
Renormalization.
So renormalization, so for the it's not exactly a linear self-similarity, but almost, right? Asymptotically linear. Okay, so perhaps let me conclude just by indicating a connection between hyperbolicity of such Siegel disk renormalization fixed points And the theorem of Duff and Cherita on the existence of Julia sets of positive measures. So this is what Misha mentioned in his talk, that it uses all kinds, it uses several kinds of renormalization. Let me just give you a brief indication of how I see the connection. And again, Mitsu should talk about this in much more detail. So, okay, so the ID's program was to create Julia sets of positive measure corresponding to Kramer points whose continued fractions look like very lacunary sequences. So you fix some n, you have a lot of n's, and then you insert infinity, which just means you insert, say, some huge number here as needed, and then again n, and a lot of them, and then again infinity, and so on. Okay? And of course, choosing infinities to be large enough natural numbers, you can always assure that this is, that the Bruno condition fails, that you'll get a Kramer point.
The strings of bands get longer and longer?
Right, the strings get longer and longer, and the point is not to lose measure. And from thesis of Cherita, it was known that you could go from a seagull to parabolic and not lose measure. So you could take, infinitely many n's, which of course has positive measure. That's a seagull disk. So the filled Julia set has interior. You could truncate this and put infinity somewhere. Still has positive measure, but the point is you don't lose much. So what needed to be shown is that as you put further, that you can iterate the procedure. And to iterate the procedure, you actually need to know that as you renormalize this and you zoom in, the Julia set of this basically occupies all of the plane. I mean, not just positive measure, but everything. And of course, once you know hyperbolicity of the fixed point, you know what you're going to converge to if you let the number of n's here go to infinity. What you are going to converge to is a point which should correspond to backward infinite continued fraction, which ends with infinity. So this is infinite backwards. And this is just a point this is the parabolic point in the unstable manifold of the fixed point, of the renormalization fixed point. So if this is the renormalization fixed point, F star, for the seagull disk, this is stable direction. This is the local unstable manifold. This is the parabolic fixed point. This is this. Okay? And then that's like Kurt's tower with the parabolic base, and it's easy to show that the Julia set of that occupies the whole plane. Well, I mean, full measure. Okay, so, all right. So in the remaining minute or so, let me just conclude by saying thank you to Dennis, and thank you for opening this wonderful world for us. And it's a lot of fun to be talking about this. It was even more fun to be doing it. It's just really great stuff. So thank you and happy birthday.
Question?
Sorry, about...
No problem.
Once again, it will be a stupid question about the couple of the pairs of commuting maps. Why the same techniques doesn't apply more or less immediately the conjecture, the universality conjecture for maps that have for maps that are analytic on the left and on the right.
So there is a part of
Here's
this.
the question.
So he wants to know why we cannot do, at least I cannot do the circle maps whose exponent is not an odd integer.
Or unimodal maps with exponent which is not an even number.
So
Well, why did he ask that?
I don't know, probably because it's a really nice open problem. And
It wasn't fake. It's great open problem. There's no huge missing idea.
yeah, so there are various missing and ideas, I think. So it depends which direction you want to go. So for example, if you want to prove a perturbative result, say in this setting, then that looks accessible, but then you need a space in which hyperbolicity is still true, in which you can consider non-integer exponents. That's not immediately, it's not immediately obvious, at least.
The odd exponent here and the even in the other cases because these maps have
Analytic.
They have analytic models.
Yeah, but
They have analytic models that they can be complexified.
But you can complexify on the left and on the right. And you have the same flag.
True. So you can still.
That's piecewise.
Yeah, you could still define something that's piecewise analytic. I mean, this whole story up to the butterfly pictures could still be pushed through, but then an idea is missing.
No, they're missing. Yeah. I mean, the hard estimates are there, but the actual algebraic ideas.
Right.
It's the soft part that's missing.
Yeah, that's absolutely right. All the bounds, all the estimates, everything works independently of the.
So if you understand well, by this term, you can only use cylinder renormalization when the entries in the continuous fractions are large enough or something.
No, cylinder renormalization for critical circle maps works for all continuous fractions.
I see. So you can see
you don't need any assumption.
So if you have the golden mean fixed point, you can see that has a fixed point of an operator in a Planet space.
Yes.
Oh.
So this works, like I said, this works without any assumptions. You just need to say the map and the Epstein plus. You don't need.
So I don't understand the theorem of that.
The theorem is that if you have a map and the Epstein plus, and that's and it's renormalizable enough times, let's say rational rotation number if you like, then you maybe need to renormalize it a couple times and you will have cylinder renormalizable map.
So K naught there is the number of normalizations, not the continuous fraction.
Yeah, this has nothing to do. Yeah, perhaps I should have made this an So okay, so those who know that this picture is guaranteed when you are close to parabolic. If you take something which is very close to this hypersurface, this is a perturb for two-cylinder. But in fact, you have this globally in the Epstein plus, which is a bit of a miracle that it always happens, right? But it does.
You can't talk until Saturday. Sorry.
But he wants me to talk.
Can you mention your work with Dennis Sullivan about the golden mean?
Oh yeah, well thanks.
Out of my reach.
Thanks for reminding. If I can mention some other of my own work, I'm always glad to. It's absolutely. You can keep me here for as long as you like. So we had a project with Dennis Gaidashev, who used to be in Toronto, is now in Uppsala, on doing numerical and rigorous computer-assisted proofs for the golden mean fixed point for Siegel disk. So Mitsu's work gives hyperbolicity for continued fractions with large enough n. And it's interesting to see what happens for the golden mean. And we are able to at least do everything numerically. And it's not, the problem is you have this rather, I mean, you trade one trouble for another when you switch from commuting pairs to cylinder renormalization. You have this change of coordinates, which is uniformizing this quotient Riemann surface. It's not very pleasant. So when you are in the parabolic case, then you have other tools to deal with this, right? Then there's a nice, other nice techniques to deal with the coordinates. But here you're very far from the parabolic. So already computing this is a challenge. So we are able to do this. If you're interested, I can show you pictures of what the fixed point Siegel disk looks like and tell you what the eigenvalues are and so on. We didn't quite push this to a computer-assisted proof, but given a big enough computer to run the program, presumably doable. But it's nice that this can actually be computed. you know, and I knew this is all true in theory, but to actually see that it converges when you do this on a computer is quite another thing.
So, I mean, at the beginning of this kind of, these things were discovered in the 70s, it was a very interesting epistemological point that here were precise statements that were true and not proven, because these numerical experiments showed they were true. So it's a very interesting epistemological point. Again, you don't usually don't have that in math. You don't know if the Riemann hypothesis is true. So we didn't usually know whether the Priori was true. It could be false. These things were true. And yet, there was the techniques that were kind of around were not adequate. I mean, this is like a little before however we would use or something like that. So it's very interesting. Here we have a statement that's true, and there's some proof that the techniques that are existent. So you know, there has to be somehow it was an interesting motivation is to not just to prove it, but actually find these new things that are going to prove it. It's very interesting.
Then, if I can, I think it's even more because there was the numerical indication that some facts were true, and also a potential explanation scheme was looking on the earlier theory in physics. But that explanation scheme was kind of foreign to motivation, and in fact, lots of people began to understand that it might be true when you began to reinterpret that as a dynamical version of reality, so that it began to be more familiar to mathematics. So then the renormalization explanation, which for physics was almost a proof that it will be true, was essentially a retaining for the mathematician because it was so foreign.
Okay, so why don't we thank the speaker again?